Astronomers detected a galaxy older than the universe itself, and nobody can explain how. There is a small dot of light in the data from the James Webb Space Telescope that, by every law of cosmology we currently understand, should not be there. It looks ordinary at first glance. A faint smudge in an infrared image. The kind of object an astronomer might glance at and move past, on the way to something more dramatic. But the team that found it did not move past. They went back to it. They measured it again. They measured it a third time. And what they kept finding, with increasingly precise instruments, was a number that should not have been possible. The galaxy is too old. Not too old by a little. Too old by hundreds of millions of years. The stars inside it appear to have been forming and aging for longer than the universe, at the redshift we are observing them at, has actually existed. It is called the JADES galaxy. And in January 2026, an even stranger one was confirmed, a galaxy now called MoM-z14, observed as it existed only 280 million years after the Big Bang. The team that wrote the paper called it, in the title itself, a cosmic miracle. Tonight, we are going to walk through what that phrase actually means. Why a small group of cosmologists, including some at the IAC, have published peer-reviewed papers measuring stellar populations in alien galaxies that are, by their best calculations, older than the universe was when those stars formed. We are going to walk through the 4 leading explanations the field is currently arguing about, why each one solves part of the puzzle and not the rest, and why a small number of physicists are quietly suggesting that something foundational about cosmic time may need to be rebuilt. So get comfortable. Settle into your chair. Let the lights go low and let the world outside fade out, because this is going to be a slow, careful walk through one of the strangest unresolved problems in modern astronomy. By the end of tonight, you will understand exactly what the math is failing to do, why it is failing, and where the field actually stands, which is nowhere clean, nowhere certain, and nowhere comfortable. If this is the kind of slow, honest science you want at the end of your day, please consider hitting subscribe. It costs you nothing, and it genuinely helps the channel reach more people who are looking for exactly this kind of quiet at the end of their day. Now, let's begin. There is a galaxy in the data. I want to start by walking you into the James Webb archive the way an astronomer would. Imagine a database of millions of small infrared images, each one a tiny patch of sky, captured by an instrument floating 1,000,000 miles from Earth at the second Lagrange point. The instrument itself is the size of a tennis court, with a primary mirror almost 7 meters across, sitting in the cold vacuum of deep space, shielded from the sun by a 5-layer sunshield the size of a tennis court itself. It cost $10 billion. It took 25 years to design and build, and every day, it streams data back to Earth that is changing what we thought we knew about the universe. Most of the objects in the James Webb images are familiar. Stars in our own galaxy. Nearby galaxies, similar in shape to the Milky Way. Distant galaxies, smaller and dimmer, but still recognizable. Each one fits into a long-established family tree of cosmic objects, sorted by distance, by age, by type. Astronomers who specialize in this field can glance at most images and quickly identify what they are looking at. And then, every once in a while, an object shows up that does not fit. The first one we are going to talk about tonight was found by a team led by Kevin Heinlein at the University of Arizona, working as part of the JADES survey. JADES stands for the James Webb Advanced Deep Extragalactic Survey, a multi-year project specifically designed to find the most distant galaxies in the universe. The team had already broken records before. In 2022, they identified a galaxy called the 2022 record holder, which appeared to exist about 325 million years after the Big Bang. At the time, that was the most distant galaxy ever observed by any instrument in human history. Then, in early 2024, they found something stranger. The new galaxy was small. It was faint. It was not particularly impressive in any visual sense. If you saw the actual James Webb image, you would see a single pixelated red dot in a field of similar dots. Nothing about it would tell you, just by looking, that it was different from the dozens of other red dots around it. What made it unusual was its redshift. Let me explain what that means in plain language, because it matters for everything we are going to discuss tonight. As light travels through the expanding universe, its wavelength gets stretched. Imagine a sound wave being stretched as the source of the sound moves away from you. The pitch drops. Light works similarly. The further the light has traveled, and the longer ago it was emitted, the more stretched it becomes. A blue galaxy nearby looks blue. The same galaxy, observed across billions of light years, looks redder. The further away it is, the redder it appears. Astronomers measure this stretching with a number called Z, the redshift. For a galaxy in our local neighborhood, Z is close to 0. For a galaxy halfway across the observable universe, Z is around 1 to 2. For the most distant galaxies ever observed before James Webb, Z was around 11 to 13. Each step up the redshift scale represents a leap further back in cosmic time. The team measured this new galaxy at Z equals 14.32, which means the light we are seeing from this galaxy left it when the universe was only 290 million years old. I want you to sit with that number for a moment, because the implication is strange. The universe today is 13.8 billion years old. This galaxy is being observed at a moment when the universe was 290 million years old. That is roughly 2% of its current age. We are looking at the universe in its infancy, before the era when most cosmologists expected complex galaxies to exist at all. Let me put 290 million years in human terms. If the universe were 100 years old, we would be looking at it during its first 3 weeks of life. 3 weeks. That is the moment in cosmic history we are observing. The first 3 weeks of a 100-year span. And yet here it is. A real galaxy. Confirmed by spectroscopy, glowing brightly enough to be detected from across nearly the entire observable universe. It is called the JADES galaxy, and it is the first piece of the puzzle we are going to spend the rest of tonight working through. But the puzzle does not end with its discovery. The puzzle is what is inside it, what the universe is supposed to be doing at 280 million years old. Before we go any further, I want to slow down on what cosmologists actually expected to find at this epoch, because the contrast matters. According to the standard model of cosmology, the universe began 13.8 billion years ago in an event we call the Big Bang. For the first 380,000 years after that, the universe was a hot, opaque plasma. Temperatures were in the thousands of degrees. Light could not travel freely because there were no stable atoms yet. Photons kept bouncing off free electrons, scattering in every direction. If you could somehow have been there to watch, you would have seen a uniform glow filling all of space, with no structure, no individual objects, just a hot fog. Then, at 380,000 years, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This event is called recombination, and it released the cosmic microwave background. The faint glow we still detect today as the echo of that moment. It is the oldest light in the universe, and it is everywhere. Right now, while you are reading this, photons from that ancient moment are passing through the room around you. After recombination came the cosmic dark ages. The universe was full of neutral hydrogen, but no stars yet. No galaxies. Just gas, slowly clumping under gravity, getting denser in some places, thinner in others. Imagine a uniform fog slowly developing pockets of higher density, with the spaces between them growing emptier. This phase lasted roughly 100 to 250 million years. Around the 100 million year mark, the densest pockets of gas finally collapsed into the first stars. These first-generation stars, which cosmologists call population 3 stars, were enormous, hot, and short-lived. They burned through their fuel in millions of years rather than billions, and they died as supernovae, seeding the surrounding gas with the first heavy elements. Carbon, oxygen, iron. None of these existed before this moment. Every atom of carbon in your body, every oxygen molecule you have ever breathed, traces back to a star that died at this stage of cosmic history or later. Then, slowly, over the next several hundred million years, the first galaxies began to form. The picture cosmologists had built, based on observations and simulations stretching back decades, was that early galaxies should be small, dim, gas-rich, and chemically primitive. They should be unsorted, irregular, still in the process of becoming galaxies in any organized sense. Tiny clumps of stars and gas, forming faster than gravity should reasonably allow, but still nothing like the structured spiral or elliptical galaxies we see closer to home. Let me say that again because it matters for what comes next. At 290 million years after the Big Bang, the universe was supposed to be home to first-generation stars, primordial gas, and the earliest unsorted clumps of matter beginning to form protogalaxies. Not mature galaxies, not bright galaxies, not galaxies producing complex chemistry, not galaxies massive enough to dominate James Webb's field of view. That is the picture the textbooks describe. That is the picture every major cosmology course teaches. That is the picture that has been refined by hundreds of papers over decades. And that is the picture James Webb has been quietly contradicting since 2022. Now, with that contrast in mind, let us walk back to the JADES galaxy and look at what is actually inside it. Because the redshift, the distance, the time we are observing it at, those numbers are striking on their own. But what makes the galaxy a real puzzle is not when it exists. It is what it contains. The JADES galaxy, the record breaker. So let us return to the JADES galaxy with the textbook picture in mind. This galaxy exists at 290 million years after the Big Bang. By the standard model, it should be small, dim, primitive, and unsorted. What it actually is, by careful measurement, is the opposite of all of those things. It is bright. The team that confirmed it noted that its luminosity was significantly higher than predicted by any leading galaxy formation model. We are not talking about a slight excess. We are talking about a galaxy producing several times the light that simulations predicted should be possible at this epoch. Whatever processes were happening inside it were producing photons at a rate the standard model could not easily account for. It is more massive than the early universe should be capable of producing. Mass estimates for galaxies at this distance carry significant uncertainty, but the lower bounds on the JADES galaxy are already higher than expected. And the spectroscopy revealed something even stranger. The galaxy contained oxygen. Let me slow down on what that actually means, because it is the heart of why this matters. Oxygen, in cosmic terms, is a second-generation element. It does not exist at the moment of the Big Bang. The Big Bang produced only the lightest elements, hydrogen and helium, with trace amounts of lithium. Everything heavier than that, including oxygen, including carbon, including the iron in your blood, was forged inside stars, through fusion, and released into space when those stars died in supernovae. For a galaxy to contain detectable oxygen, an entire generation of stars must have already lived and died inside it. I want you to feel the weight of that, because it is the heart of the paradox. In a universe 290 million years old, the JADES galaxy had already produced enough stars, lived through enough supernovae, and accumulated enough heavy elements to show up clearly in James Webb spectroscopy. The math, as a small group of cosmologists have started saying out loud, does not add up. Let me put the timeline in perspective in 3 different ways, because the number 290 million years is hard to feel by itself. First, in cosmic fractions, the universe today is 13.8 billion years old. 290 million years is roughly 2% of that. Second, in human terms, if the universe were 100 years old, we would be looking at this galaxy at age 3 weeks. 3 weeks. To produce a galaxy that is bright, massive, and chemically evolved. Third, in stellar lifetimes, even the most short-lived first-generation stars need at least a few million years to form, fuse hydrogen, and explode. To enrich a galaxy with oxygen requires multiple cycles of formation and death. Doing this in 290 million years is, by current models, almost the maximum theoretical rate. The JADES galaxy looks like it pushed that limit. A team led by Brant Robertson at the UC Santa Cruz, who co-authored the confirmation paper, noted that the team's first reaction to the data was disbelief. They went back to the telescope. They re-observed the object. They cross-checked it against other instruments. They considered every possibility, including that it might be a foreground galaxy mistakenly assigned a high redshift, a kind of cosmic mirage. The galaxy survived every test. It is real. It is at Z equals 14.32. It is at 290 million years after the Big Bang, and it is far too mature for that epoch. That single galaxy, by itself, would already have been a problem worth investigating. But it did not stay alone for long. MoM-z14, the new record holder, January 2026. If the JADES galaxy was the moment cosmologists started getting nervous, the moment they actually had to start writing papers with words like miracle in the title, was when the next record breaker was confirmed. In April 2025, a team led by Rohan Naidu at the MIT pointed James Webb at a small object that had been flagged in earlier surveys as a possible target. The object was even fainter than the JADES galaxy. It was even smaller, about 50 times smaller than the Milky Way by their estimate. To put that in perspective, the Milky Way contains roughly 200 billion stars. MoM-z14 contained, at the moment we are observing it, perhaps a few billion. A small galaxy by modern standards. But for a galaxy at Z equals 14.44, It was unexpectedly luminous. When the spectroscopy came back, the redshift was higher than the JADES galaxy. Z equals 14.44. That is 280 million years after the Big Bang. 10 million years earlier than the JADES galaxy. 10 million years sounds like a lot, but at this epoch of cosmic history, it represents a meaningful step backward into territory cosmologists thought might be barren of mature galaxies altogether. The galaxy was confirmed in January 2026 in a paper published in the Open Journal of Astrophysics. The paper's title was unusually direct. It was called, "A Cosmic Miracle, a Remarkably Luminous Galaxy at Z equals 14.44 Confirmed with James Webb." When astronomers use the word miracle in a paper title, they are not being poetic. They are signaling, in academic language, that the object is genuinely difficult to explain. The word is doing real work. It is communicating to the rest of the field that this object pushes against what current models predict in ways that the authors themselves cannot fully reconcile. Let me break down what they actually found, because the details are striking. MoM-z14 is small, but it is bright. The team measured emission lines indicating the presence of nitrogen and carbon, which means it had already produced multiple generations of stars to forge those elements. Peter van Dokkum, one of the co-authors, noted that the emission lines indicated a galaxy that was very young, with a rapidly increasing rate of forming new stars. The team also noted, importantly, that there was not much neutral hydrogen gas surrounding the galaxy, which is itself surprising. The very early universe is supposed to be filled with neutral hydrogen, and a galaxy at this epoch should be embedded in a cloud of it. So we have a paradox inside a paradox. The galaxy itself is at the very edge of cosmic dawn, and yet its stars have already been through cycles of formation, death, and chemical seeding, and the gas around it does not look like the primordial gas we expected to find at this epoch. The math does not add up. By the standard model, you cannot have multiple generations of stars within 280 million years of the Big Bang. You can have one generation, maybe 1.5. You should not have evidence of ongoing chemical enrichment at this epoch, and the surrounding gas should be neutral and dense, not whatever it actually is around MoM-z14. 3 weeks into the universe's life, by our earlier comparison, MoM-z14 already looked like it had lived through its own cycles of stellar evolution, and we have known about it, with confirmed spectroscopy, since January. The strange thing is, this is not the most controversial measurement in the field. That comes next, and it does not come from the JADES galaxy or MoM-z14, the two record breakers. It comes from a different sample of galaxies, slightly closer to us in cosmic time, where the measurement is not just unusual but quantifiably impossible under the standard cosmological model. To understand it, we have to step back and walk through how astronomers measure the age of the universe in the first place, and how they measure the age of stars in galaxies billions of light years away. Because once we have those two numbers, the comparison is going to produce a result that the field has been quietly arguing about for almost 3 years. How we measure the age of the universe. To understand the next step in this puzzle, I need to slow down and walk you through how astronomers actually measure cosmic time, because the precision matters for what comes after. The 13.8 billion year figure for the age of the universe is not a guess. It is not even an estimate. It comes from multiple independent lines of evidence that all converge on roughly the same number, with extraordinary precision. The most precise measurement comes from the cosmic microwave background, the leftover heat of the Big Bang, which we can still detect today as a faint glow filling the sky in every direction. The Planck satellite, a European Space Agency mission, mapped this glow with extraordinary precision between 2009 and 2013. The pattern of small temperature variations in the microwave background, fluctuations of about 1 part in 100,000, encodes information about the geometry, density, and expansion rate of the universe. From this, cosmologists can derive the age of the universe to within a fraction of a percent. I want you to feel how precise that is. The age of the universe, by Planck's measurement, is 13.787 billion years, with an uncertainty of about 20 million years. To put that in perspective, that is a precision of about 1 part in 700. We know the age of the universe better than we know the average lifespan of a redwood tree. There is one complication I want to mention briefly because it will matter later. There are 2 different methods for measuring the expansion rate of the universe, the Hubble constant, and they disagree slightly. Measurements from the cosmic microwave background give one value. Measurements from nearby exploding stars, called Type 1a supernovae, give a slightly different value. The difference is small, perhaps a few percent, but it has been persistent and has not gone away with better data. This is called the Hubble tension, and it has been a quiet concern in cosmology for about a decade. Some researchers think it is a hint of new physics. Others think it is a measurement systematic that will eventually be resolved. For now, set that aside. The point is that the age of the universe is one of the best measured numbers in modern science. It is not 13.8 billion plus or minus several billion. It is 13.787 billion plus or minus 0.020 billion. We know it to within 20 million years. Now, the same precision applies in reverse. When we observe a galaxy at redshift Z, we can calculate how old the universe was at the moment that light was emitted. This is straightforward physics, derived from the same expansion model that gives us the 13.8 billion year age, applied at earlier times. At Z equals 8, the universe was 600 million years old. At Z equals 14, it was 290 million years old. These numbers are not estimates. They are derived directly from the same model that the rest of cosmology uses every day. This is the standard cosmological model. Cosmologists call it lambda CDM, or lambda cold dark matter. It includes dark matter, dark energy, and the geometry of an expanding universe. It has been tested against thousands of independent observations, and it has held up remarkably well. It is, by any reasonable measure, the most successful theory in cosmology since general relativity. So when I say the universe at redshift 8 was 600 million years old, I am using the same model that the rest of cosmology uses. And when I say the math does not add up, I mean it does not add up within that model. The implication is significant. To make the math add up, you have to either revise our measurements, revise our stellar models, or revise the cosmology itself. The stellar population age problem. Now we turn to the other half of the puzzle, which is how we measure the age of stars in a galaxy billions of light years away. This is harder than it sounds. We cannot fly to the galaxy. We cannot examine individual stars. The galaxy is so far away that, even with James Webb, we cannot resolve individual stars or stellar clusters within it. The entire galaxy is a single point of light to our instruments. What we can do is collect light from the galaxy, spread that light into a spectrum across different wavelengths, and compare the shape of that spectrum to models of what stars of various ages should produce. The key feature astronomers look for is something called the Balmer break, a sudden drop in light intensity at a specific wavelength caused by hydrogen absorption in stellar atmospheres. The shape and strength of the Balmer break depends on the average age of the stars in the galaxy. Old stellar populations have a strong, well-defined Balmer break. Young stellar populations, full of hot, blue, recently formed stars, have a much weaker one. Let me put that in plain language. When a population of stars is young, it is dominated by hot, bright, short-lived stars that produce a smooth spectrum across most wavelengths. When the same population is older, those bright young stars have died, leaving behind cooler, redder, longer-lived stars whose atmospheres absorb light at specific frequencies, including the Balmer transitions in hydrogen. The presence and strength of those absorption features is what tells you the age of the population. This technique is called spectral energy distribution fitting, or SED fitting. It is the standard technique. It works reliably for nearby galaxies, where we can cross-check the result against direct observations of individual stars. It has been refined over decades, with thousands of galaxies cross-checked between methods. When astronomers apply SED fitting to James Webb galaxies at redshifts of 6 to 10, they can derive an estimate of how old the stellar populations inside those galaxies are. Stated simply, they can ask, given the shape of the spectrum we see, how long must these stars have been forming and evolving to produce this pattern? The answer comes out as a probability distribution, with a most likely age and a confidence interval. For most early galaxies, the answer comes out reasonable. The stars look young, consistent with the universe being young at that epoch. No paradox. But for some early galaxies, the answer does not come out reasonable. For some of them, the answer is older than the universe at the redshift we are observing them at. I want to be careful with that statement, because it would be easy to oversell. Let me be precise. The team that has pursued this most rigorously is led by Martín López Correduara at the IAC. They have published multiple peer-reviewed papers on the topic, in respected mainstream journals. They are not announcing a paradigm shift. They are not claiming the standard model is wrong. They are saying, in careful academic language, that with the best modeling tools available, certain galaxies appear to contain stellar populations whose age is incompatible with the standard cosmological timeline. The math, by their measurement, does not add up. Lopez-Corredoira's measurement, the central scandal in 2023. A team led by Evo Lab at Swinburne University identified 13 candidate massive galaxies in the James Webb CERS survey, all at average redshift around Z equals 8. That places them at roughly 600 million years after the Big Bang. The galaxies were unusually massive, with stellar masses estimated at around 10 billion times the mass of our Sun, on average. To put that in context, our own Milky Way has a stellar mass of roughly 60 billion solar masses, accumulated over more than 13 billion years. These early galaxies were already at 1/6 the mass of the Milky Way, in less than 5% of the time. That alone was already a problem for galaxy formation models, because by the standard model, galaxies that massive should not exist that early. Lab's paper drew significant attention, and several follow-up studies probed the result. Lopez-Corredoira and his colleagues took the next step. They asked, given that these galaxies exist, how old are the stars inside them? They applied careful SED fitting to the spectra. They modeled extinction by interstellar dust using multiple extinction curves to test sensitivity. They modeled emission from active galactic nuclei to check for contamination. They used realistic stellar population synthesis codes, the same tools used for nearby galaxy studies. They tested the results against independent calibrations. They ran the analysis multiple ways to check robustness. And the answer they got, with 95% confidence, was that the stellar populations in these 13 galaxies had ages between 900 million and 2,400 million years. I want you to sit with that for a moment. 900 million years is the lower estimate. 2,400 million years is the upper estimate. Across the 13 galaxy sample, the average age came out around 1.5 billion years. And these are galaxies in a universe that, at redshift 8, was only 600 million years old. Let me say that one more time, because the implication takes a beat to land. The stars inside these galaxies, by careful peer-reviewed measurement, look on average 900 million years older than the universe is supposed to be at the moment we are observing them. The math does not add up. By 300 million years on average. In the most extreme cases, by 1,800 million years. If the Lopez-Corredoira measurement is correct, the stars inside these galaxies would have had to begin forming several hundred million years before the Big Bang itself, which, in the standard model, is impossible. The Big Bang is the start. Nothing came before it. There is no time available for star formation that began earlier, because there is no earlier. The team has been careful to flag every assumption. They note that the result could come from systematic errors in the modeling. They note that AGN contamination could mimic an old stellar population. They note that the result is provisional. The IAC issued a public statement when the work was first reported, emphasizing that the finding was attention, not a definitive proof of new physics. But they also note, in their published papers, that no combination of standard adjustments fully accounts for the tension. The math, as best they can calculate, does not add up. The 4.7 Sigma galaxy in a 2026 follow-up paper published in Monthly Notices of the Royal Astronomical Society. Lopez-Corredoira and his collaborators went further. They expanded the analysis to a sample of 31 galaxies between redshift 6 and 10. They refined the modeling. They tested for every plausible source of systematic error they could identify. They allowed for AGN contributions. They allowed for varying dust treatments. They tested the impact of the V-shaped spectral energy distribution that some early galaxies show, which can complicate age estimates. They controlled for as many degeneracies as they could. The average age of the 31 galaxies came out to 610 million years, with a 95% confidence interval of 310 to 920 million years. The age of the universe at the average redshift of the sample is roughly 700 million years. So most of the sample is actually consistent with the standard model. The math, on average, does add up. This is an important and honest result. The team did not cherry-pick. They reported the average. But within the sample, one galaxy stood out. This galaxy, one of the redder ones in the set, was measured to have a stellar population age incompatible with being younger than the universe at greater than 4.7 sigma confidence. I want to slow down on that number, because 4.7 sigma is not a casual claim. Sigma is a measure of statistical confidence, a way of asking how likely a result is to be just random noise rather than a real signal. 1 sigma is roughly a 32% chance that a result is just statistical noise. That is a low bar. 2 sigma drops that chance to around 5%. That is the bar most fields use to call something interesting but not yet trustworthy. 3 sigma is the threshold below which most fields will not call something a real signal at all. 4 sigma is around a 1 in 16,000 chance of being noise. 4.7 sigma is roughly a 1 in 1.3 million chance of being a measurement error. For comparison, the discovery of the Higgs boson at CERN in 2012 was announced at 5 sigma. Physicists consider 5 sigma the gold standard for declaring a new particle. The single galaxy Lopez-Correduaras team identified is just below that threshold. 1 in 1.3 million chance that the result is statistical noise. Not a coincidence. I want to be careful with the implications, because the team itself is. They note in the paper that systematic errors in stellar population models could still account for the tension. They specifically mention TPAGB stars, a type of late-stage stellar evolution that produces complicated spectral features, as a possible model uncertainty. They check whether including TPAGB effects changes the result. It does not. They check whether AGN contamination could account for it. The galaxy does not show clear AGN signatures. They check whether dust extinction could explain it. The dust would have to be implausibly extreme. They have, in short, tried to make the result go away, and it has not gone away. So here's where the field stands. There is at least one galaxy in the James Webb data whose stellar population age, by careful peer-reviewed measurement, is incompatible with the standard cosmological timeline at 4.7 sigma. The result is provisional. It is one galaxy. It could still turn out to be a measurement artifact, but it has been published. It has survived peer review. It is sitting in the literature, waiting to be either confirmed or explained away. And the field is not yet done either. I want to pause here for a moment, because the next part of tonight is going to walk through 4 different attempts to explain what is happening. And before we go into them, I want to give you a sense of where we actually stand. We have a small set of galaxies in the James Webb Archive whose existence is uncontroversial, but whose properties, when carefully measured, fit awkwardly with the standard cosmological timeline. We have a series of peer-reviewed papers, by careful researchers at major institutions, documenting the tension. We have one specific galaxy where the tension reaches the level of statistical significance that physicists usually take seriously. What we do not have is consensus. The field is divided, not loudly, but persistently. Some researchers think the answer is in the dust. Some think it is in the black holes. Some think it is in the speed of early galaxy formation. A small number think it is in the cosmology itself. And almost all of them agree that the answer, when it comes, will require either better data, better models, or both. So with that in mind, let us walk through the 4 leading explanations one at a time. We will see what each one solves, what each one fails to solve, and where the field actually stands at the end of it all. Explanation 1. Dust and measurement error. Now we turn to the 4 leading explanations for why these results might be wrong, or might be right but compatible with standard cosmology after all. We will walk through each one, see what part of the puzzle it solves, and see why none of them has cleanly resolved the question yet. The first explanation is the most natural one for any astronomer to reach for. It is dust. Interstellar dust, made up of small particles of carbon, silicates, and ices, absorbs short wavelength light and re-emits it at longer wavelengths. This is called extinction, and it is one of the trickiest effects in observational astronomy. Dust reddens the light from distant objects. Without correcting for it, you can mistake a young blue galaxy obscured by dust for an old red galaxy with no dust at all. The 2 scenarios produce light that, on the surface, looks similar. The difference between them is captured in the precise shape of the spectrum, but that shape is not always easy to measure cleanly at high redshift, where the signal is weak. In the early universe, the question of how much dust exists, and how it is distributed, is genuinely uncertain. The first heavy elements have not had much time to form. Dust grains take time to assemble. The first generation of stars produces some dust when they explode, but it takes additional cycles of stellar formation and death for dust to become widespread. So the assumption has often been that early galaxies should be relatively dust-free, which simplifies the modeling and gives cleaner age estimates. Here is where the explanation enters. If early galaxies actually contain more dust than we have assumed, then the apparent age of their stellar populations would be overestimated. The dust would make young stars look old. by reddening their light in a way that mimics the spectral signature of old stellar populations. The galaxies would look older than they are. The math would seem not to add up, but only because of the dust. This is a real effect, and it does account for some of the tension. Several recent studies have argued that better dust modeling brings the implied stellar ages of some early galaxies back into agreement with the standard model. When astronomers use more sophisticated dust attenuation curves, including effects from different grain compositions and geometries, the implied stellar ages drop. Some of the apparent paradox dissolves under this treatment. But there's a problem. Let me explain. The Lopez-Correduara papers explicitly model dust extinction. They use multiple extinction curves to test sensitivity. They check the results against nearby galaxy calibrations. They allow for unusually high dust scenarios. They specifically test whether physically reasonable amounts of dust can account for the implied ages. And the tension does not dissipate. For the 4.7 Sigma galaxy specifically, the team tested whether any reasonable amount of dust could account for the measured age. The answer was no. Even with implausibly extreme dust assumptions, the galaxy still came out too old. So dust solves part of the puzzle. It does not solve all of it. Several galaxies in the James Webb sample show ages that come back into agreement with standard cosmology after careful dust correction. But others do not. The math, for those, still does not add up. Explanation 2. AGN mimicking old stars. The second explanation focuses on a different source of contamination. Active galactic nuclei. An active galactic nucleus, or AGN, is a supermassive black hole at the center of a galaxy that is actively accreting matter. The matter falling into the black hole heats up to enormous temperatures, glows brightly, and produces a distinctive spectrum that includes emission across a wide range of wavelengths. Some AGN are surrounded by dense gas clouds that absorb and re-emit the light, producing what are called red AGN. Here's where the connection to our puzzle comes in. The spectrum of a dust-enshrouded red AGN can, in some cases, mimic the spectrum of an old stellar population. Both produce the kind of reddened light pattern that SED fitting interprets as old stars. The Balmer break that astronomers look for as a marker of old stars can be partially mimicked by certain AGN configurations. From the outside, looking only at the spectrum, the two scenarios can look similar. If many of the James Webb early galaxies are actually red AGN, not galaxies dominated by old stars, then the apparent age of their stellar populations is an artifact. The black hole is doing the work, not ancient stars. This explanation has been actively explored. James Webb has revealed an entire class of objects called little red dots, which are unusually red, compact, and abundant in the early universe. They were a surprise. Nobody had predicted that the early universe would be full of these compact red sources. Some researchers have argued that many of these are AGN, not normal galaxies. Others have argued that they are unusual baby galaxies, still in the process of formation. The debate is active. The 2024 paper by Wang and colleagues, focused on two galaxies common with the original lab sample, concluded that the most likely fit for those galaxies includes a dominant red QSO component, with an underlying stellar population significantly younger than 900 million years. By their interpretation, the galaxies are AGN-dominated, and the apparent age problem is reduced. They specifically identified broad Balmer emission lines in one of the galaxies, which is a fairly clean indicator of AGN activity. This is a real and important contribution. For some galaxies, AGN modeling brings the data back into agreement with the standard model. But again, there's a problem. Not every James Webb galaxy with anomalously old stellar populations has the spectral signatures of an AGN. Some of them, including the 4.7 Sigma galaxy, were specifically tested for AGN contamination. The team checked broad emission lines, which are a hallmark of AGN. They checked variability over time, another AGN indicator. They checked the X-ray properties when available. The 4.7 Sigma galaxy did not show clear AGN signatures. So AGN solves part of the puzzle. It does not solve all of it. Some galaxies are likely AGN-dominated, and their stellar age estimates need to be revised. Others appear to be genuinely stellar in origin, and for those, the math still does not add up. Explanation 3. Revised galaxy formation models. The third explanation is the one most cosmologists prefer, because it changes the smallest amount of physics. The idea is simple. The standard model of cosmology, lambda CDM, is correct. The age of the universe is correct. What needs to be revised is our model of how galaxies form inside that cosmology. Specifically, this explanation argues that early galaxies formed faster, more massively, and with higher star formation efficiency than current simulations predict. The first generations of stars were larger, brighter, and produced heavy elements more efficiently. The gas in early galaxies converted to stars at unprecedented rates. By the time we observe these galaxies at redshift 1408, they have had enough time, within standard cosmology, to produce the mass, brightness, and chemistry we see, but only because everything happened more aggressively than we modeled. The cosmology is fine. The astrophysics inside the cosmology is what needs work. This explanation has been pursued by several theorists. Avis Heidekel and colleagues at the Hebrew University of Jerusalem have proposed feedback-free starbursts, where rapidly collapsing gas converts to stars without the usual delays from radiation feedback. Normally, when stars form, the radiation pressure they produce pushes back on the surrounding gas and slows additional star formation. This is a self-regulating loop. But under certain conditions in the very early universe, the gas may have been dense enough to overcome this feedback, allowing star formation to proceed at rates much faster than usual. If this is right, early galaxies could have built up mass far quicker than current simulations allow. Others have explored super-Eddington accretion onto early black holes, which would make the central engines of galaxies more powerful than thought and contribute more luminosity per unit mass. POP3 stars, the first generation, may have been even more massive than current models assume, with individual stars reaching hundreds or even thousands of solar masses. Such stars produce heavy elements very rapidly when they die, dramatically accelerating chemical enrichment. Some models even invoke primordial black hole seeds, formed before any stars existed, to explain the rapid emergence of large galactic structures. If these revisions are correct, then there's no paradox. The galaxies are exactly as old as the standard model says they should be. They just formed in ways we did not anticipate. The cosmology is fine. The astrophysics inside the cosmology needs work. This is the field's preferred quiet answer. It is the explanation that requires the least disruption to existing physics. It keeps lambda CDM intact. It only asks us to update our simulations of early galaxy formation to allow more aggressive processes than we currently include. But here is the limitation. Even with the most aggressive revisions to galaxy formation, the math has not yet been made to work. Simulations that include feedback-free starbursts, super-Eddington accretion, and revised initial mass functions still fall short of producing the level of maturity we see in the most extreme cases. The 4.7 Sigma galaxy, in particular, is hard to reconcile even with maximally aggressive star formation. The NIDA paper on MoM-z14 specifically notes that producing the observed luminosity requires star formation rates near or above the maximum the early universe is thought to allow. So galaxy formation revision solves part of the puzzle. It probably solves most of the easier cases. It has not yet solved the hardest cases. The math, for those, still does not add up. Explanation 4. Cosmology itself needs revision. The fourth explanation is the one most cosmologists do not want to discuss, because if it is correct, the implications are large. The idea is that the age of the universe itself is wrong. Not by a small amount, by a lot. And that means the standard cosmological model, lambda CDM, needs to be modified or replaced. This is the explanation that takes the Lopez-Corredor measurements at face value. If the stars inside early galaxies really are 900 to 2,400 million years old, when the universe is supposed to be only 600 million years old, then either the stellar age measurements are wrong, or the universe is older than we think. Several theorists have explored this direction. The most developed proposal is the CCC plus tired light model, developed by Rajendra Gupta at the University of Ottawa. CCC stands for covariant coupling constants. The model proposes that fundamental physical constants, like the speed of light and the gravitational constant, may have evolved slightly over cosmic history. Combined with a tired light component, where photons lose energy gradually as they travel across the universe, the model produces a different relationship between redshift and time. In Gupta's model, the universe is not 13.8 billion years old. It is 26.7 billion years old. At redshift 10, it would have been 5.8 billion years old, not 470 million. At redshift 20, it would have been 3.5 billion years old, not 180 million. There would be plenty of time for galaxies to mature, for stars to live and die multiple generations, for chemistry to evolve. The James Webb anomaly disappears entirely under this model, because the time available for galaxy formation is many times what the standard model allows. Other proposals exist alongside Gupta's. Modified gravity models, such as F of R theories, attempt to alter the equations of general relativity at large scales. Dark matter and baryon coupling models propose new interactions between dark matter and ordinary matter. Dynamical dark energy models suggest that the cosmological constant, the energy density driving the universe's expansion, has changed over time. Each of these tries to account for the James Webb observations by adjusting the underlying cosmology in some specific way. I want to be careful here, because this is the most controversial part of the discussion. Most professional cosmologists do not accept these proposals. The standard lambda CDM model is supported by an enormous amount of independent evidence, including the cosmic microwave background, the abundances of light elements produced in Big Bang nucleosynthesis, the large-scale distribution of galaxies, and gravitational lensing observations. Replacing it requires not just explaining the James Webb anomaly, but also reproducing every other successful prediction the standard model makes. That is an extremely high bar. Most alternative cosmologists fail at it. They explain one anomaly and break two others. But here's the thing. A small number of cosmologists, at respected institutions, are taking these proposals seriously enough to publish them in peer-reviewed journals. They are not crackpots. They are professionals who have looked at the data and concluded that the tension is real enough to warrant exploring alternatives. Gupta's CCC plus tired light papers have been published in mainstream astronomy journals. The work has been cited, debated, and engaged with by the wider community. So cosmological revision is the most extreme explanation. Most physicists reject it. Some take it seriously. None has yet succeeded in producing a fully consistent alternative cosmology that fits all the data, including the James Webb observations. The math does not add up under the standard model. It also does not yet cleanly add up under any of the proposed alternatives. Why none of the four cleanly wins? So where does that leave us? The picture is heterogeneous. Different explanations work for different galaxies. Dust modeling fixes some cases. AGN contamination accounts for others. Revised galaxy formation handles many of the moderate anomalies. Cosmological revision is held in reserve by a small minority for the most extreme cases. What no single explanation does is cleanly account for the entire pattern. If you take the James Webb early galaxy sample as a whole, you find galaxies whose anomalies fit different categories. Some are likely AGN-dominated, with their stellar age signatures coming from accreting black holes rather than old stars. Some are dust-affected, with their reddened light mimicking old stellar populations. Some are probably explained by faster-than-expected star formation, with their early maturity reflecting more efficient galactic assembly than current simulations capture. And a few, including the 4.7 Sigma galaxy, resist all of these explanations. The math does not add up under any single hypothesis. It only adds up if you allow yourself to apply different fixes to different galaxies, which is not yet a satisfying solution. A clean theory should explain the whole pattern, not require a different patch for every anomalous case. When physicists encounter a situation where every solution works for some cases and fails for others, the suspicion is usually that the underlying picture is incomplete in a deeper way that none of the partial fixes is quite reaching. Let me be precise about what this implies. It does not mean lambda CDM is wrong. The standard model has survived many anomalies before. It does mean that the James Webb data, taken together, is harder to digest than any single explanation suggests. The field is in the position of having an unusual amount of data that pulls in slightly different directions, and not yet a story that pulls them all together. This is where the field actually sits in 2026. Multiple partial explanations. No clean one. A handful of galaxies that resist every standard fix. A growing body of evidence that something, at minimum, about early galaxy formation needs revision. And an open question, behind closed doors at conferences, about whether the revision will eventually have to reach further than star formation models alone. That is a strange place to be. It is not crisis. It is not breakthrough. It is something more uncomfortable than either. The kind of slow accumulation of unresolved data that, in the history of physics, has sometimes preceded major revisions and sometimes faded quietly when the systematic error was finally found. Where exactly we are headed, nobody can say. What this looks like in the history of science, I want to step back from the technical details for a moment and place this kind of moment in a wider context. The history of science is full of anomalies that initially looked like measurement errors and turned out to be the first signs of a deeper revision. The detection of the cosmic microwave background by Arno Penzias and Robert Wilson in 1965 began as a faint hiss in their radio antenna at Bell Labs in New Jersey that they spent months trying to eliminate. They cleaned the antenna. They removed pigeon droppings from the inside. They checked every cable. The hiss would not go away. They were not looking for the leftover heat of the Big Bang. They were trying to fix what they thought was a hardware problem. It was, instead, the first detection of the oldest light in the universe. The discovery that the universe is expanding, made by Edwin Hubble in 1929, came from observations that initially looked like noise in the data. The universe was expected to be static. Hubble's measurements, when they came in, suggested it was not. It took years for the field to accept the result. Even Einstein, when first confronted with the data, was reluctant to abandon his static universe equations. The detection of dark matter began as an inconsistency in the rotation curves of galaxies, first noticed in the 1930s by Fritz Zwicky and confirmed in the 1970s by Vera Rubin. The galaxies were spinning faster at their edges than the visible mass could account for. Most physicists initially assumed it was a measurement error. It was not. It was the signature of an entirely new kind of matter that we still cannot directly detect, only infer from its gravitational effects. The history is also full of anomalies that turned out to be measurement errors. Faster-than-light neutrinos from CERN in 2011, eventually traced to a loose fiber optic cable in the timing system. The BICEP 2 announcement of primordial gravitational waves in 2014, eventually attributed to galactic dust contamination in the foreground. Real cracks in physics are rare. Spurious cracks are more common. Most anomalies fade quietly when the systematic error is found. The James Webb Early Galaxy anomaly currently sits in the middle. It is too early to say which category it belongs to. The measurements are real. The tension is statistically meaningful. The proposed explanations all solve part of the problem and not the rest. The field is divided in a way that has not yet resolved. What the history teaches us is patience. Anomalies of this kind take years, sometimes decades, to resolve. The community has to accumulate more data, refine the models, and either find the systematic error that explains the result or accept that the underlying physics needs revision. Both outcomes have happened before. Both could happen here. We are at the beginning of that process, not the end. I want to mention one more parallel from history, because it is relevant. In the 1990s, there was a brief period where measurements of the oldest globular clusters in our galaxy gave ages that, in some analyses, came out larger than the age of the universe. The numbers were close. The error bars overlapped, but the central values disagreed, and for a few years the field had to take seriously the possibility that the standard cosmological model needed major revision. That tension was eventually resolved, mostly through better measurements of the Hubble constant and refined stellar age models, both of which shifted the numbers into agreement. The crisis dissolved. The James Webb tension may resolve the same way, or it may not. There is no rule that every apparent crack in physics turns out to be a measurement error. Sometimes the crack is real, and the field is to redraw the map. Distinguishing the two outcomes, in any given case, takes years. What would resolve this, so what would it actually take to settle the question? Better data is the first answer. The Roman Space Telescope, which is scheduled to launch as early as late 2026, is designed to survey large patches of sky in the infrared. It will produce a much larger sample of early galaxies than James Webb has, by orders of magnitude. James Webb can stare deeply at small patches. Roman will sweep wide areas. With more galaxies in the sample, the statistical power increases. If the 4.7 sigma anomaly is a real feature of the universe, we should find more of them as the sample grows. If it is a one-galaxy fluke, the largest sample should average it out and the apparent tension should fade. Within the next few years, we should know which. Better stellar models are the second answer. Stellar population synthesis is a mature field, but it depends on assumptions about star formation history, metallicity, and late-stage stellar evolution. Improvements in any of these areas could shift the apparent ages of distant galaxies up or down. The TPAGB question, the AGN modeling question, and the dust treatment question are all active areas of research, with new papers appearing every few months. The community is iterating. The models a decade from now will be better than the models today, and some of the current tension may dissolve as those models improve. Better cross-checks between methods are the third answer. If different techniques for measuring stellar ages, applied to the same galaxy, give consistent results, the result is hard to dismiss. If they disagree, the problem is somewhere in the methods themselves. Independent age estimates using globular cluster comparisons, dynamical mass measurements, and kinematic indicators could help triangulate the truth. So far, the cross-checks have not converged into a single picture. I want to be honest about what we know versus what we suspect. We know the James Webb galaxies exist. We know their redshifts to high precision. We know that careful spectral analysis, applied with peer-reviewed methods, suggests stellar populations older than the universe at the redshift of observation in at least some cases. We know the result is provisional and survives at the 4.7 sigma level for at least one specific galaxy. We do not know which of the four explanations is correct. We do not know whether the result will survive the next decade of observations. We do not know whether the standard cosmological model will need revision, or whether the apparent paradox will be resolved by improvements in our modeling of stars, dust, and black holes. What we can say is that the field is paying attention. Conferences are being organized around early universe tensions. Papers are being submitted. Telescopes are being pointed. The question is being taken seriously, by serious people, in serious venues. That is the actual state of the field. Calibrated, uncertain, genuinely open. There is something almost reassuring about that, when you think about it carefully. Modern science, in its most active corners, is not a finished story. It is a process. The textbooks we have today are not the textbooks our grandchildren will have. Somewhere in the James Webb archive, in the papers that are being written this year, in the simulations that are being refined this month, the next chapter of cosmic history is being slowly worked out, and we are alive to watch it happen. Closing the Big Bang model has been one of the most successful theories in the history of science. For nearly a century, its predictions have been confirmed by observation after observation. The cosmic microwave background, the abundances of hydrogen and helium produced in Big Bang nucleosynthesis, the large-scale structure of galaxies, woven across the universe in filaments and voids, the accelerating expansion of the universe, discovered through observations of distant supernovae. The model has held up across an extraordinary range of measurements made by an extraordinary range of instruments. We were not wrong about the Big Bang. We may have been wrong about some of the details of what came right after it. The next time you step outside on a clear night and look up at the deep sky, I want you to think about something. The faint galaxies you cannot see, the ones at redshifts far beyond what your eyes can detect, are still up there. They are real objects, sending light across nearly the entire age of the universe to reach the small infrared sensors of an instrument floating 1 million miles from Earth. Those photons left their galaxies more than 13 billion years ago. They have been traveling, undisturbed, through the vacuum of space, for almost the entire history of the cosmos. And now they are arriving at James Webb, one by one, telling us things about the early universe that we did not expect to hear. In some of those galaxies, by careful measurement using techniques that work reliably for galaxies closer to home, the stars appear to have been forming and evolving for longer than the universe at that epoch should have allowed. The math does not add up. And that fact, that small unresolved disagreement between data and theory, is one of the most quietly interesting cracks in modern cosmology. We do not yet know what is on the other side of it. It might be a measurement issue, eventually traced to a subtle problem in how we model dust, age n, or stellar evolution at high redshift. It might be a galaxy formation issue, eventually solved by simulations that capture some early universe process we have not yet implemented. Or it might be something deeper, a hint that our picture of cosmic time itself needs revision. Whichever direction the resolution comes from, the universe is going to feel slightly different on the other side of it. The story we tell about how galaxies formed in the first hundreds of millions of years after the Big Bang will be slightly more sophisticated, or slightly more strange, than the story we tell today. That is where we are. That is where the field actually sits. And tonight, that is where we leave it. Until next time.